So your third computer assignment is due Friday. Your fourth computer assignment isn't posted. Right. Yeah, the day before Thanksgiving. No problem. You're welcome. That's part of the quality service you receive. Okay, so the fourth assignment is going to be focused on filtering, and we're going to hopefully spend a little bit of today and then Friday and then maybe even Monday kind of going through my little filtering spiel. Although I cover it pretty effectively in the book. What the homework assignment does is it basically gives you two signals. One's a sawtooth, one's a square wave, and both of them have unknown noise sources in there. And one has one kind of noise source and the other has another kind of noise source. And your goal is to A, use frequency analysis to figure out what the noise is, and B, build some sort of filter to kill the noise. And so that's about it. And I'll be showing you a bunch of tools to do that. Like this Matlab is just chock full of tools to make that kind of analysis work. All right? But before we get on to that, and we will get on to that, I did want to do sort of one last convolution example, only because it underscores a point that I was trying to make on Monday. And what I wanted to do was to convolve, and stop me if you've seen this one before. I want to convolve this signal with this signal. Rectangle against a rectangle. Have you played this game before?
No.
Okay.
Yeah, we actually did. There was one that was at a higher amplitude than the other one.
Oh, one was at a bigger. Okay. So let's just run through it anyway, because a little repetition probably wouldn't kill us. And what I'm going to do here, I'm going to specify that they're the same size. Actually, I want to convolve this thing against itself. All right. And what's that?
It's going to be a triangle.
It's going to be a triangle. Why do you think that's good? So why a triangle?
They're the same width, so it's going to be, the only point of overlap is going to be a finite space.
Good. Typically, when convolving means multiplying and integrating. And when you convolve against a constant, you can expect to effectively just integrate the other function. So because I'm convolving against a constant, I can expect that this function will be integrated. And you know when you integrate a constant, you get a line. Okay. So let's just kind of walk through it, though, just to double check. I don't know. Where do you want to center this thing? At 0, 1, 2? Where do you want to center this thing? 0? You unadventurous. Okay, 0. All right, let's make it have a width of, I don't know, A. Oh, you want to go like that. Okay, nice. Well, let's make it have an area of 1. So what would the height have to be? 1 over 2A. Oh, boy. We're going to do that. Okay, and should we center this one at the same place? Or do you want to center this someplace else? Center it at pi? What's wrong with you? Okay. All right, no, let's do it. Whatever. Be careful what you ask for. So that's pi plus A, pi minus A, 1 over 2A, T, T. All right? No, I said actually, you know what? I said I wanted to convolve it against itself. Now, this is a shifted version of itself. Okay, I'm going to center it at 0. Yeah, let's center it at 0. And I'll tell you why when I'm done. Like, I think my reason will be a little bit more apparent when I'm finished. Yeah, all right. Well, let's be unadventurous. Nice handwriting because I'm having my picture taken, right? So good board technique. This is sloppy. There we go. All right, we try, you know. Okay, so we got to do the whole convolution flip and slide nonsense, right? So let's make our I like to do this little column notation. It helps me. So I'm going to start by drawing x of tau. So this is now x of tau relative to tau. That's 0 minus A to A. Now to get my h of t minus tau, I'm going to take my h, I'm going to flip it, and then I'm going to shift it by t units. Okay, so when I do that, I'm going to get this. So this is h of t minus tau. And where is so did I put t here? This is tau. I beg your pardon. So this is on the axis of tau. I need a landmark. Where's the center of this thing located? It was at 0, but then I shifted it by t units. So it's at t. Okay, so that's the key to making this analysis work. All right? If you screw this step up, you're done. This is the critical step. Everything after this is sort of plug and chug. So we flipped it. When I flipped it, the center was still at 0. And then I shifted it by t units. Now the 0 center is located at t units. So wherever the 0 point is, becomes t. Okay? So if this is t, where's this point right here? T plus a and t minus a. All right. So for the scenario that you're looking at here, we'll call this case case A. Is there any overlap between between x of tau and h of t minus tau? Do they overlap? Is there any non-zero overlap?
No.
No. Because there is no non-zero overlap, when I multiply those two functions together, because remember the convolution integral says take x of tau, h of t minus tau, and multiply. So when I multiply this function against this function, what am I going to get? 0. And when I integrate, I'm going to get 0. Okay. So for case A, y of t is going to equal 0, the result of my convolution integral. Okay? Now, what values of t will be applicable? Can we agree, I need some colors to make this point. So, can I agree that as long as this point here, as long as this point is less than that point, there will be no overlap? We agree? So, this list of conditions on which that will hold, that means that I'm going to scratch paper over here. That means that t plus a has to be less than minus a. So therefore, t has to be less than minus 2a. So this condition holds for t less than minus 2a. Okay, so let's start to draw my answer. Oh, we got a... Actually, that's not too bad. I was going to say we got one of our lousy boards today. Okay, so if I'm plotting y of t, then I've got minus 2a, okay, and my answer is 0 as long as I'm less than minus 2a. You with me? Okay, good. That's case A done. So I start with this, my block at negative infinity. I get 0, 0, 0, 0, 0, 0. And then all of a sudden, this block and this block start to overlap. That's your next case. That's case 2. So let's take this block, shift it over a little bit, and now we'll have that. So that's your case B.
Why is it t plus a has to be less than negative a?
Because this point, so the question is, why is t plus a less than negative a? And the answer is that case A is the case when there's no overlap between the two functions. And that's going to happen as long as this edge is to the left of that edge. And that happens when t plus a is less than negative a.
So if you make the mistake and you label t plus a over to the left and t minus a to the right.
Yeah, exactly. Like if you labeled this point as t plus a or whatever, like that's it. That's why I said you've got to get that step right, or otherwise you're done.
No.
All right, there's no fixing that. Okay, so in case B, what am I going to get? What do I get when I multiply those two functions together?
Partial overlap.
I've got a partial overlap. So remember, so again, scratch space. The convolution integral is the integral of x of tau, h of t minus tau, d tau. So when there's non-zero overlap, what is x of tau equal to? Yeah, although I think we decided to call it 1 over 2a, right? The constant 1 over 2a. I don't know why. Oh, all right, we wanted to have a unit area on each of them. I promise it's going to work out for the best. So x of tau is 1 over 2a. What's h of t minus tau? What's h of t minus tau? Here's your function. It's the same thing. It's a constant. 1 over 2a. Now, here's the tricky bit. What are your limits of integration? Where will the non-zero overlap occur? Now, this is... Right, it's going to... Exactly. So the non-zero overlap starts here, because that's where this function starts, and it ends here. So this is the time, that's the overlap that I want to integrate. So the back end is at minus a, the front end is at t plus a. So putting all that together, we go from minus a to, where am I? I'm lost now. T plus a. We good? Is this a disaster? No, because 1 over 2a squared, constant, you're welcome. Okay. So that becomes 1 over 2a squared, which is a constant. And then I've got integral of 1, which is just t. Sub in the limits of integration. I have t plus a minus a, which gives me t plus 2a. So here's my case B. Y of t equals 1 over 2a squared times t plus 2a. What's that look like? What's the shape of that? It's a line with a slope of... Right. It's a line with a slope of 1 over 2a squared. And so is that a positive slope or a negative slope? Nice. Okay. So some sort of line, and we'll flesh that out in a second. Let's just talk about what ranges of t this applies for. I know that this case B has to start where the previous case ended. So I know this has to apply for t greater than minus 2a. Right. T has to be greater than minus 2a. But where does the party end?
No, 0. T is equal to...
So if I keep shifting this over, let's see, at some point, when you say 0, what do you mean by 0?
When t is equal to 0.
Ah, good. So this, right, this case will end when I shift this block over so that it's exactly underneath of the original block. Because after that, if I shift it further than that, then the limits of integration on my integral would have to change. So I'm going to shift this over till it's centered under the original block, and that will occur when t lines up with 0. So let's draw this. So I've got a line starting at minus 2a, ending at 0. So there's a line. Okay, and let's see. What is the value of this equation at t equals 0? Right. So this will be 1 over 2a. Tremendous. Nice. Just out of curiosity, what does this equation predict for t equals negative 2a for this point? 0. This is important, right? The way convolution works, unless you're convolving impulses or something, which screw everything up, as long as there's no impulses, it's interesting that you don't get discontinuities in your convolution integral. So in other words, what the convolution predicts for this function at minus 2a and what the convolution predicts for this function at minus 2a give you the same value. So by the same token, when I do my next integral for this section, you better be sure that that convolution integral will also predict 1 over 2a at t equals 0.
Is there always continuity in convolution?
Again, as long as you're not convolving impulses, yes. Once you start convolving impulses, it gets a little trickier, but not by
So
much.
are you gonna have like a less than or equal to sign on one of either?
Somebody always asks me that. Yeah, sure. You know, whatever. But yes. There you go. It doesn't matter. Yeah, that's one of those details that mathematicians like sweat, and I don't. 'Cause I don't. Whatever. It's just it's a detail. Okay, so let's move to case C. So case C now is going to be when my rectangle is shifted over even more. All right, see how this is different now? Right. Right. Well, first of all, let's just set up the integral. Then we'll define what the limit, what values of t it applies for. So x of tau is still 1 over 2a. H of tau is still 1 over 2a. So the only detail I need to sweat now is the limits of integration, which doesn't have to be hard, right? Where am I going to integrate this thing from? I'm integrating it from this point, which is where the overlap starts, until this point, which is where the overlap ends. So it starts at t minus a, and it goes till a. So this point is, where's my black marker? This point is t minus a, and this is a. So that's your limits of integration. T minus a to a. So the 1 over 2a squared comes out again. And let's see, what are we left with in the integral? It looks like it's going to be a minus t plus a. So that's going to be 2a minus t. Okay, so there's my third case. So y of t equals 1 over 2a squared, 2a minus t. All right, so what does this function predict at t equals 0?
1 over 2a.
Hey, how about that? Right, as advertised, 1 over 2a. It's a line with a negative slope, so that's good. What range values of t is this going to apply for? Like, how far can I shift this case to the right before this integral doesn't apply anymore?
T minus a less than a.
Right, as long as t minus a is less than a, I can run this integral. So, in other words, as long as t minus a is less than a, I'm good to go, which means that for this case, t has to be less than 2a. So 0 less than t less than equal to 2a. You happy? I did less than equal. Don't mention it. Okay, so here we go. 2a. And after that, what am I going to get? Do I actually need to integrate the last case out? No. After that, the rectangle will be so far shifted that I'm going to get 0 again. And we're done. Now, we did this example for like 2 reasons. One is I just wanted to practice convolution, and I think we were okay on that. Convolution doesn't have to be hard. It's not mechanistically complicated. It just requires discipline with like dotting the i's and crossing the t's. Like you can't wing it. You can sometimes eyeball it and like expect the rough shape of the answer, but it really rewards the detail-oriented person. Because you can see that this kind of all hinged on getting the limits of integration right, and the t's and the zeros, and you can't just sort of wing it. It's not hard. We didn't do anything like ridiculously complicated. You just had to be detail-oriented. So there's that. So the next thing that was interesting is that we had the continuity for each of my 3 functions, for each of the 4 functions that we had. Here we had y of t was 0. Here we had y of t equaled, right, so it was 1 over 2a squared times, was it t plus 2a? 1 over 2a squared t minus, nope, 2a minus t, and then 0. So all four of those functions agreed at the interface points like what they should be. So there were no discontinuities. I like that. Okay. But there's a bigger point that I want to make. And that has to do with the lecture we looked at on Monday. So, according to the lecture we had on Monday, what is the Fourier transform of this triangle? It's a sinc function with less high frequencies. How do you reckon that?
We took away the high frequency. Took out the corners.
We took off the corners, right? We had that. Can we actually get the actual Fourier transform of this?
Yeah, using derivative property.
Right, so if you use the derivative property, so let me just do this real quick. So if you do the derivative property, so that's the derivative. Okay, what's this number here? What's that slope?
1 over 2.
Nope.
1 over 2.
Nope. Oh, actually, well, maybe it is 1 over 2a.
1 over 2a squared. 1 over 2a squared. Yeah.
It's a rise of 1 over 2a divided by a run of 2a. So this is 1 over 2a squared, and this is negative 1 over 2a squared. And this goes from minus 1 over 2a to 1 over 2a. No, whoa. This goes from minus 2a, 0, to 2a. So putting all this together, when we take that Fourier transform, so what's the Fourier transform of this rectangle? It's a sinc with a width of a, with a half width of a, and an area of
1 over 2a.
It's the area of 1 over 2a. Okay. So, is that right? Yeah, area of 1 over 2a. So putting it all together, it's 1 over 2a sine a omega over a omega. And then we have to shift it to the left by a units. So that's e to the j a omega.
Shouldn't we make it
Oh.
10?
What's that?
Oh, no.
No, because it's shifted to the left. And then we got to do this guy, which is minus 1 over 2a sine a omega over a omega, and then that shifted to the left, so it's e to the minus j a omega. And then we made this awesome observation that I could factor out 1 over 2a sine a omega over a omega. And what was I left with? E to the jaw minus e to the minus jaw. And what's the final step that I need to do?
Put it all over j omega.
Right, I've got to reintegrate it to get my function back, which means in the Fourier space I'm going to divide by j omega. Stick with me, I promise this is going to be worth the payoff. You're working hard and I appreciate it. Okay, what does this nonsense in the numerator do for me? Sine. So my numerator is equal to 2j sine a omega. Watch this. The j's cancel. Oh, that's so nice. The 2's cancel. Okay. So look what's left. Look what's left. Sine a omega. Hold on. No. Sine a omega over a omega times sine of a omega over a omega.
Can you express that as a hyperbolic sign?
It's possible it could be done. I don't know how. Right, and this is the smooth. This is like the sinc function. Remember, like we talked about, but smooth. Like the high frequencies are suppressed. But more interestingly than that, let's make the point. We learned that if I take a signal x of t and take its Fourier transform, and a signal h of t and take its Fourier transform, then I learned that if I convolve x of t and h of t in the time domain, then what do I do to their Fourier transforms? I multiply. So remember, we learned that convolution in the time domain is multiplication in the frequency domain. All right? So, is that what I've done here? Yeah, absolutely, right? I took rectangle, we gave it area of 1, right? So the rectangle was sine of a omega over a omega. I convolved it with itself. Therefore, if I do rectangle convolve rectangle, then the Fourier transform had darn well better be sinc function times sinc function. Have a nice day. Isn't that sick? It works. Like every time I do this, it blows my mind. It's not okay that this works. All right? But it works. So just another example of convolution in the time domain corresponding to multiplication in the frequency domain. And as we learned on Monday, it works the other way around. We actually learned that if you take two signals and multiply them in the time domain, what happens in the frequency domain? You convolve. Okay, and we saw that in the context of truncating a signal. If you take a signal, like a cosine, and you truncate it, that means like you get, you make it finite duration, then effectively you're multiplying that infinite cosine with a square wave. And in the frequency domain, that has the effect of convolving the Fourier transform of the cosine with the Fourier transform of the rectangle pulse.
Isn't there a 2 pi
Here? There might be a constant somewhere. Who knows? I'm not going to sweat it. It depends whether you do it with respect to omega or f. People throw around 2 pi's. I'm not too worried about those constants. So let me just kind of, so anyway, that's all I really wanted to say about convolution. I think once you kind of understand this, you sort of have it for the most part. I do want to say a couple things though. Like I gave this on a test once, and I thought it was a cool problem because you can actually get most of it without having to do any calculus, right? So what if I give you that signal and tell you to convolve it with this signal?
We know the Fourier transform for both of them. The Fourier transform of the sine is just going to be an impulse. And the Fourier transform of the square wave is going to be a sinc. So if we multiply them in the frequency domain,
It's just a shifted sin function.
Exactly. Well, but this is a single period. I'm not talking about an infinite cosine.
Oh, okay.
Although we could do the infinite cosine case.
So what you're saying is actually it's already a square wave multiplied to a sine function.
Yeah. So there's a couple ways we could think our way through this.
So it's a square. So it's a square wave that's multiplied to a sine function, and then you convolve it to another square wave.
Right. Right. So we can do this a couple ways. Let me just start by what I would say the quick and dirty approach. So, well, you could always just write the integral, right? You could do that, and you would get the right answer. But you remember what I told you? I said that if you convolve against a constant, then effectively, what are you doing to your original function? Integrating. Right? That's the example we just did. We took a square pulse, convolved it against a square pulse, so we integrated. anytime you integrate against this function, against a constant, then effectively what you're doing is you're taking constant times this function, which just gives you that function back, and then integrating that function. So if I convolve these, I can just eyeball this and say, well, for t less than 0, I'm going to get nothing because there's no overlap. Then when t is between 0 and 1, I'm going to be effectively integrating that sign. And what do I get when I integrate sign? Cosine. And that makes sense, right? First I'm going to have, and if I integrate sine, I get, hold on, now you flustered me. What did you do?
It is negative.
It's negative cosine.
Negative.
Negative cosine? That doesn't
Oh,
make-
yeah, it is negative cosine.
Hold on. I just lost my sea legs. If you integrate sine,
Zero cosine, integral
It's negative.
Integral of sine is 0.
well, hold on a minute. Hold on. I need 30 seconds of personal time. Instructor break.
So the derivative of 0 is sine then.
Hush. You're integrating sine of 2 pi t from 0 to 2 pi tau, 0 to t d tau. So integral of sine is negative cosine? Yeah, so negative 1 over 2 pi cosine 2 pi tau from 0 to t 2 pi t minus e to the cosine of 0 is 1. So when t is 0, I get 0. Weird.
When t is 0, you get minus 1, right?
Yeah, minus
Minus-
1
minus
times 1.
Oh, it's a cos. Right. It's a cosine that's shifted up. That's why. It's a negative cosine that's shifted up. So you're going to get basically, because when you first integrate this thing, you've got nothing. That's why I was confused. You get nothing, then you're getting more and more and more and more until finally you've got about as much as you're going to get. So here you go. And then you start to get less and less. You're adding less and less to your integral. And then you start to subtract from your integral. And you get back, eventually you've integrated out everything that you put in, so you get 0. So what you're getting is a cosine. Just draw that a little nicer for you. Ah, come on. Third time's the charm. Oh, okay, you deserve better. Don't take a picture of that. Okay. All right. So that would get you all the way to t equals 1, where there'd be like a full overlap between them. And then the rectangle would start to shift off of it, and you'd get the equal and opposite effect. So then you'd start to get kind of like a negative cosine that would dip that way. You can kind of eyeball your way through it. But I do like the idea of what you were saying originally, which was to recognize that this is a sine times, this is a sine times a rectangle, which means in the Fourier space, you know you're going to get basically a sinc pulse and a sinc pulse. And then you're convolving it with this guy, which means that in the frequency space, you're multiplying it with a sinc pulse. So if you take this and do a pointwise multiplication with your sinc pulse, you'll get the Fourier transform of your final answer. I don't know if that actually helps you any, but it's just another way of visualizing the problem.
Would you get one on top of the other?
Yeah, you'd get literally one on top of the other, and you'd attempt to multiply them.
Actually, that would be.
It would be.
Oh, no, because the actual question you want.
I don't think it would actually help
The answer
you.
would be in the time domain.
Yeah,
So then you'd have to bring that
back into the time domain. That'd be hopeless. But if I asked you for the answer in the frequency domain, you could do it that way.
Yeah, that's.
Okay.
It will still be hard.
Yeah, it would be ugly. Okay. So, questions on convolution. What am I going to do with 13 minutes left? I know what I'll do. We'll start to talk about filters. All right, and on Friday we'll actually come and play with some filters in Matlab. So, I don't know what you guys studied in Circuits 2. Yes, spare me the peanut gallery. I can only imagine, but just so I know where to take this conversation, what do you know about filters?
They remove certain frequencies.
They remove certain frequencies, great. From like a mathematical perspective.
Pretty much, it's your output from some element, from measuring the voltage at some element of the circuit, some component.
Right. So you're taking you have a circuit that you're driving, you're going to measure the voltage at some other point in the circuit, and you may retain the one set of frequencies from your input, but lose another set of frequencies. Okay, so how about this? Have you heard of the term poles and zeros?
Yeah, absolutely.
Do you know what they mean?
Wow.
Okay, I'm getting a soft yes on poles and zeros.
On the top, poles on, all right, the
They're like
denominator,
the
sorry.
kind of frequencies actually.
Okay, good. Well, whatever. Okay, do you know, have you heard the term Bode plot?
Yes.
Okay, good. Have you heard of the term 20 dB per decade?
Yes.
Very nice. Have you heard of, do you know what to do when you have a system that has like a whole bunch of poles in it? Like let's say 4 poles and 3 zeros.
Yeah.
Would you know how to look at that?
You mean how to plot?
Yeah, like how to figure out what kind of filter it is, how to plot it, yeah.
Yeah.
Okay, so we're going to do a little bit of
You
review.
get the standard form, and so
You find the K, you find the first pole and the second pole.
Okay, so you're familiar. We'll refresh.
Second pole before the dB.
Good.
First pole.
All right, have you heard of the difference between an elliptic filter and a Chebyshev filter?
no.
Ah, okay, so I do have some value I can bring to this. Chebby. Okay, have you heard of
How about Butterworth?
Butterworth? Yeah, well, that's the Chebyshev lecture. There's Chebyshev, elliptic, and Butterworth. It's just 3 different flavors of filter. And have you heard of, what's the last thing I meant to tell you? Oh, the relationship between transfer function and the differential equation.
Yeah. Still a plus.
Yeah, Laplace Transform.
Yeah.
Okay. So I have a better idea now of like which parts I need to spend a ton of time on and which parts I need to I can just sort of breeze over. So let me just start with this. Let's look at a circuit that we've all seen before. Okay, not because I'm trying to educate you on it, because I know you all know the answer, but just so that we have a common point to move forward on. So suppose I take an AC signal and put it into this low-pass filter. Okay, we've looked at this low-pass filter before. I think the difference between what we're doing this term and what you did last term is that last term in Circuits 2, you learned, you basically talked about how does this circuit respond to inputs that are at different individual frequencies. So your input was always a cosine at different frequencies. This semester, what we're essentially saying is your input can be any signal. The difference this time around is that your input can be any signal, but we know that any signal can be represented as just a bunch of cosines at different frequencies. And we know how to take a signal and deconstruct it into a series of cosines. And then the math that we've learned will tell us how each of those cosines will fare as it gets put through this filter. Okay, then you rebuild them at the output. You say, okay, well, I got these frequencies. Those ones were rejected. What's my output going to look like? So very quickly, again, I know this is probably a little bit review. So let's say this is V source, this is V out, this is your resistor, this is your capacitor. So if we were to write a differential equation for this, right, the differential equation would essentially say that the current through the resistor has to equal what? The current through the cap, and the current through the cap is C dV out dt. And if I reorganize that, I get dv out dt plus v out over rc equals v supply over rc. Okay? Now, this equation completely describes the system. I want to make that point. This completely describes the system. So, in other words, if you know the differential equation, you know everything. Right? You can get the transfer function. You can get the impulse response. You can get the step response. You can get the response to any arbitrary input. Right? The whole goal of this exercise is to anticipate how a system will behave in response to an input. Okay? There is a time domain approach to answering that question, and there is a frequency domain approach to answering that question. All right? This differential equation has everything built in it to answer the time domain question. Right? What's your output in response to a particular input? Right? You don't need anything else than what's here. And the other bit that's interesting is that it's entirely characterized by the value RC, the time constant. Right? If you know the time constant, that's it. That's the only parameter of this signal. Now, let's talk about the transfer function. If I take this differential equation and take the Laplace transform, or even the Fourier transform, I mean, it doesn't really affect it too much. What do I get? I get S V0, because it's the derivative of V0. Remember, derivative is the same as multiplying by j omega in the frequency domain. So SV0, so I'm going to make the simplifying assumption that j omega equals S. Does everybody know the difference between the Fourier transform and the Laplace transform? Really?
Why don't you, it always seems to be a discussion. Between here, recitation.
Well, I'm going to have a whack at it too.
The Fourier is purely imaginary, and the Laplace is complex.
Right. So here's what I want you to think about, and we're going to explore this a little bit. So this is your imaginary plane. So in the Fourier transform, we're decomposing signals as e to the j omega, meaning that all of the frequencies we're going to look at are j omega. They're just on this axis. Okay? So, in other words, all like real signals are on this axis. It's a little bit counterintuitive to think that real signals should have frequencies that appear on the imaginary axis. But that shouldn't surprise us if we think about it, because on like the first day of class, we talked about taking a cosine and taking that cosine and representing it as e to the j omega plus e to the negative j omega. So it's a real signal with two equal and opposite complex frequencies that are always on this axis. So for all signals, which are by definition sums of cosines, all the action is on this axis. That's the Fourier transform. The Laplace transform talks about e to the minus st, where s equals sigma plus j omega. So the sigma is a real part, and that means that gives you frequencies that could be anywhere on this plane. Yes, sir?
But when we take the Fourier transform, sometimes it's shifted, right? And we get a phase. Wouldn't that shift it a little bit from the Matlab?
No, the frequency. Remember, the magnitude and the phase tell you how much you have of a signal at a specific frequency.
Yeah.
So phase will tell you differently how much of that frequency you have, but the frequency itself hasn't changed. It's still j omega and negative j omega. Okay, so let me just do this real quick. Fourier transform. Laplace transform. SV0 plus V0 over RC equals Vs over RC. Now I can combine like terms. and solve for my transfer function, which is V out over V supply, is 1 over RC times S plus 1 over RC. Okay, so that's my transfer function. In the same way that my differential equation told me everything I needed to know to predict my output for any given input, so does this function. Also gives me everything I need to know to predict output for any given input. How? Well, if I know the Fourier transform of my input, and I multiply it by the Fourier transform, the transfer function of the system, I now have the Fourier transform of the output. We've already done that, right? That was the y of omega equals h of omega times x of omega. This is the same thing. So, does this circuit have any poles? Actually, let's start, sorry, zeros. Does this circuit have any zeros?
No.
No. Zeros are values of S that make either the numerator or the denominator equal to 0. Are there any values of S that will zero my numerator? No. Are there any values of S that will zero my denominator? Yes. Where is my pole frequency?
-1 over RC.
So we have one pole at S equals -1 over RC. So where should I put that on my plot? Where, on this imaginary plane, where does that pole go?
On the real axis.
On the real axis. Here?
No, on the other side.
Here?
Yeah.
I agree. So now we can talk about the difference between real axis and imaginary axis. Okay? Here's a pole. Okay? I cannot create, so a pole by definition means that if I were to stimulate the circuit at that frequency, then my denominator would be 0 and my output would be infinity. Right? That's what that means, right? If I were to somehow stimulate my circuit with S equals -1 over RC, my output would blow up to infinity. But can I actually do that?
No.
Is there any way I can operate my circuit at that frequency? No. Because I can only operate my circuit at frequencies that are on this imaginary axis. Because that's the only way to make real signals. Right? If I wanted to make a cosine of 1 hertz, I'd be here. If I wanted to make a cosine at 2 hertz, I'd be here. If I wanted to make a signal that was a sum of 1 hertz and 2 hertz, I'd be here and here. Okay? But I can never be here. I cannot create a real signal that will stimulate the circuit at that frequency. So that's part of the game that we're going to play. Okay? Is we're going to think about how does the circuit respond when I'm stimulating it with cosines of different frequencies, and how does this pole that's sitting out here in the nether, like I can't touch it, but it's still going to obviously affect my performance. This is going to get trippy.
But that's not well, that's just assuming that like you just have like a straight value for the light. Like what if you had like a complex pole with 0?
Oh, if I had like a pair of poles like this, yeah, we'll do that too. But it's the same concept. Even if I had complex conjugate poles, I still can't touch them. I still can't stimulate the circuit at that frequency. Yes?
What if the denominator is S minus 1 over RC?
Good luck making that circuit.
Then,
Good luck making, you can't make it.
okay, but let's just say it is negative, so then S would be positive 1 over
Then you'd have a
RC
positive
in
pole.
the real pole.
Right.
Then-
So when you take, we have to go because time is up. When you take controls, what you will learn is that as long as your poles are in the left half plane, you have a stable system. Meaning that if you put in a finite input, you get a finite output. If for some reason you screw the pooch and you get a pole in the right half plane, you're done. That means that you could put in like a nice, tidy rectangular pulse and your output would blow up to infinity. Which is generally not bad if you're trying to control something. Sorry, generally not good if you're trying to control something. Okay, thanks. I'll see you on whatever's next. Friday.